This lecture is part of an online course of multivariable calculus, and I'm going to talk about summary of all the integrals that we've learned so far. So I'm going to start with a single integral of a function of just one variable, dx over a and b. And it is what? It's the integral of a function f over an interval in R. Okay, so it calculates, if this is x-axis, this is y-axis, and I have the function f and the interval from a to b. This integral calculates the area below the graph of f above the interval a and b. Then we looked at the double integral of a function of x and y dA over the region R. It's integral of function over a region in R2. Okay, so it calculates what? I'm gonna have a 3D x, y, z, and then if I have a surface f, then the integral of f over a region R, so assume that this is your region R in the x, y plane, then the double integral of f over R calculates the volume of the solid that is bounded above by f and below by the region R. Okay, so this is B is like volume, A is just area. Okay, and if f is equal to 1, then B would be area of the region R. Okay, so I want to have more space, so let me basically move everything to the left. Okay, good. Then we studied triple integrals, which is the triple integral of a function of three variables, dv, over a solid S. It's the integral of a function f over a solid in R3. Okay, so if we have a solid like that, x, y, z, if we just have, for example, a sphere in R3, oops, like this, then this S is the region of my integration, it's a solid, and if f is equal to 1, then the triple integral calculates the volume of S for us, right? Okay, then after we studied that, we go to D, which is what? Which is just like a line integral of a function of two variables, for example, over the curve C. Then it calculates the integral of the function f over a curve C in R3 for me. Okay, so assume that I have x, y, z, then I have a solid like this, f, and I have a curve like this, for example, a curve C, And then the integral of the function over the curve C calculates basically the area that is bounded above by F and below by the curve C. It calculates the area for me. So if I want to be more specific, this line integral is similar to the single integral, but instead of interval, I have a curve. Okay? There are different kinds of line integrals. So I'm gonna say different kinds of line integrals. So what? The first one, f ds over c, which is what? Which is just the integral. So integral with respect to the arc length. Okay, to calculate that, all you need to do is to just parameterize the curve. C, plug in your parameterization into F. Let me basically write that. I'm gonna move this one a little up. Okay, so it would be the integral. I'm gonna plug in my parameterization into F, and then ds would be the length of r prime of t, and then dt, t between, for example, t1 and t2. These are the bounds for my parameterization. The other one, I can write this as f dx over c, which is basically the same thing. I'm gonna plug in my parameterization into the function, and then for dx I have x prime of t and then dt. Okay, this is basically my dx. This integral that I have in here, it would be the line integral with respect to x. Okay, and then from t1 to t2. The other one would be f dy, which is exactly the same thing, except that instead of dy, I have y prime of t dt. What are x of t, y of t? So these are basically my parameterization. If my parameterization or of t of the curve has the coordinates x of t and y of t, then I plug in this parameterization into f, and then I have the derivative of these two. This is the line integral with respect to y. And the third kind of the line integral would be the integral of f, the vector field, dr over the curve c. Okay, we're gonna do the same thing. I'm gonna plug in the parameterization into f, and then r prime of t dt. You see, I have a vector in here. That's why I need a vector for my dr, and then I have the dot product between these two. If you want to compare the line integral of a vector field, which I have derivative, with the line integral of a function, which I have the length of the derivative, because I have a function in here, I need a function in there. Okay, good. And dt from t1 to t2, and I can say that it calculates the work done by f in the direction of c. If f and c, they are in the same direction, the work is positive. If they are in the opposite direction, then the work is going to be negative. Okay, and now let's move on, and I'm gonna introduce I'm gonna basically summarize another types of integral that we study would be the double integral of f ds over solid S. Okay, it's the integral of a function x, y, and z, okay, over a surface S in R3. Okay, so we have two kinds. The first one is FDS over S, and to calculate that, I'm gonna parameterize the surface S. I need two parameters, and these two parameters are from a region D. Then it would be the double integral of f. I'm gonna put my parameterization into f, and then instead of ds, I have the length of the cross product of partial derivative of my parameterization with respect to u, with the partial derivative with respect to v, and then dA. Okay, so ds in here is the element of the surface area. I can say that it's the integral with respect to the surface area, that's capital S. Okay, and then dA in here could be du dv or dv du, based on whatever that it's easier. The integral would be over the region D. The second type of the integral would be f dot ds over the surface S. If I want to calculate that, I can write f dot nds over surface S. The surface S should be orientable surface. It means that there should be a unit normal vector at each point. Unit normal vector of S. Basically, I have a function in here. I have a vector field. I have a vector in here. I'm gonna do the dot product in here. So I have the dot product, and then how to calculate that, it would be f. I'm gonna plug in the parameterization into the vector field u and v, and then instead of nds, we calculated in the previous videos, it would be r with respect to u cross product r with respect to v. I'm gonna do the dot product with f, so I have a dot product in here, and then I get dA over the region D. Okay, and if you want to compare the line integral with that, this one calculates the flux of f vector field f through S. The orientation here is important. The direction of the curve C here is important. Okay, if the direction of C is backward, we are going to get a negative sign in here. If the orientation of S is on the negative orientation, we're going to have a negative sign in here. That was basically the summary of all the integrals that we've learned here.